Okay, this is regular physics, uniform circular motion, page 173, problem number 54. This is a challenging problem. You really have to pay strict attention to your free body diagram. All right, so we have this carnival ride. All right, it's just basically a can with the top cut off of it. 2 meters radius, and it's spinning around, and that spinning around is forcing you, up against the wall here. You're trying to wave at your friends here, but it slammed your hands against the wall here. This is a top view. Okay, so maybe you went to the carnival with your grandpa. There's a little comb over there going there. Okay, but whatever. You're smashed up against this wall, and you go, oh, that's the centripetal force. No, it's not. Your inertia says that you want to go this way. But I can't go that way because there's the steel wall of this ride in my way, right? Pressing against you. So what you have a tremendous amount of force, right, pressing you not this way, but that way. Okay, so we're given some information besides this radius. This thing tells us how fast are we spinning around. Well, it tells us that it rotates once. That's a delta theta of 2 pi. Every 0.9 seconds, that's a time. So what I have a delta theta over time. My delta theta, 2 pi radians. My time, 0.9 seconds. Divide, round off a little bit. That's 7 radians per second. That tells you how fast you're spinning around. That is angular speed. That is omega. Why is that useful? Well, because if I take omega and multiply it by my radius in meters, then I'm going to have a tangential velocity. And my tangential velocity, just like it says on my free body diagram here, right here, my speed is in this direction. Okay, but what I really want is the magnitude of this. Why? Because the magnitude I can plug into this and get my acceleration. Which direction is the acceleration? Always towards the center in uniform circular motion. Why is that important? Because if I have an acceleration, I must also have an F net in this same direction. Okay, and we need to look at this F net in order to solve our problem. Okay, now what I'm going to do is, for clarity's sake, I'm going to go from a top view. Let's go to a side view here. Here I am, being smushed up against the wall here, and I know it feels like you're being thrown this way, but that's not true. What has actually happened is this steel wall is pressing on you this way. I need an F net towards the center of the circle. Well, we've only studied 4 agents of our forces: an applied force, force of friction, force normal, force applied. This side in uniform circular motion is never 0. We've already computed this guy. Don't start mass whining. We'll get there. All right, let's finish this free body diagram. Well, what am I getting? Let's put the no-brainer. Well, I'm going to have my force of gravity, which is mg, going that way. Okay, now what is happening here? What is happening here is I am not sliding down this wall. Right? I'm sticking to this wall. Why am I sticking to the wall? Is because I'm being pressed up against the wall. All right, remember, you might be tempted to say, oh, well, this vector right here is in equilibrium with that vector. True. What is the agent of this? This is force friction to keep you from sliding down the wall on this ride. And that is still going to be equal to mu s force normal. Okay? All right. Remember, what is force normal? Force normal is perpendicular to the plane of contact. So it is this force normal that is my only vector in my free body diagram that's pointed towards the center. What about force applied? Well, there really is not a push or a pull. I guess if you wanted to say there's like a push here into the paper to make this guy go around in a circle, but that's in a different dimension, all right? So regardless of whether you think it's there or not, it's in a different dimension, so it's not going to matter. So F net pointing towards the center is just going to be all these forces, this in equilibrium, force applied, not a player, force normal this time is the only thing pointing towards the center. So when I go to Newton's law, F net equals mass times acceleration, well, that means force normal is equal to my mass times my a sub c. Well, what can I say about force normal? Force normal has a relationship to friction, according to this. Force normal is the same thing as force friction divided by mu. And that's equal to mass times acceleration. Well, let's look back at our free body diagram. What is force friction in equilibrium with? Force friction is in equilibrium with the weight, so that means the magnitude of this, the magnitude of that are the same. Well, what's the magnitude of that? mg. Now I can solve. First thing that's going to happen is mass is going to cancel. We know g, negative 9.81, or just 9.81. We already know it's down. A sub c I've already computed, so I can get this coefficient of static friction. Pretty clever. Note that this machine, the mass does not matter. What matters is speed and mu. The mass cancels out. So once I got this machine designed, it doesn't matter if it's a little kid or a big kid. It's still going to work.